cells, and simple circuits. If you have this kind of a setup, we got a dry cell, a bulb, a switch, and some conducting wires. If we close the circuit, the bulb lights. Now this is a very simple circuit. Many people would know that the cell supplies current to the circuit, and when the switch is closed, the circuit is complete. What many people can't explain, however, is what the current is and the precise role of the dry cell. But it's all got to do with charges. You know just as well as I do that charges can either be positive or negative. Electrical charges create an electric field around them, and these fields are forces that repel or attract other charged particles. Like charges repel and unlike charges attract. When enough of these particles are separated, a huge force is created, and this is what a battery does: separation of charges. So one terminal is positively charged and the other is negatively charged. But then how does that influence the flow of current? When these charges are separated this way, the negative terminal is eager to lose the negative charges of the electrons, and the positive terminal is eager to accept them. So there is a great desire for the electrons to flow towards the positive terminal, but they can only do that via an external conducting system. Put in another way, the negative terminal has a very high potential to lose electrons, while the positive terminal has a very low potential to do the same. This difference in potential creates what we call an electromotive force, or EMF. And sure enough, if we connect these terminals externally via a conductor, electrons flow from the negative terminal to the positive terminal. The amount of charge flowing through a conductor per unit time is called current, symbolized I. Remember, the quantity of charge Q is measured in coulombs, so I is equal to Q over T. Current is equal to quantity of charge over time. The SI unit of current is amperes. The SI unit of time is seconds. So 1 ampere is the amount of current generated when a charge of 1 coulomb flows in 1 second. Therefore, if 600 coulombs flow through a conductor in 5 minutes, the current can be calculated as I is equal to Q over T. 600 coulombs divided by 5 times 60, we get 2 amperes. Notice though that the battery does not create any charge. No, it only generates a driving force, EMF, that drives the electrons through the external circuit. So you can think of an electric circuit as a water circuit. The pipe has water inside, and let's say each white ball is a water molecule and the pump acts as a battery. Molecules represent our charges. You see, the pump does not create water. Water is present in the pipe. Similarly, charges are present in the conductor at all times. When the pump runs, it creates a force that drives the water around the circuit. Equally, the battery does not create any charges. It only creates a force that drives the charges. This force is the electromotive force. How does it do that? We saw it separates the positive and the negative charges and thus creates a desire or eagerness to flow. Again, if you think of these two stones in terms of falling, stone A has a very high potential to fall compared to B. And what happens is that the battery does the work of taking the stone up the cliff to create that potential difference. All forms of electricity generation work on the basis of creating an electromotive force. Of course, the larger the force, the larger the current. An electric circuit like this one allows current to move in a complete path when the switch is closed. This circuit is said to be a closed circuit. When a gap is introduced in the circuit, for instance by opening the switch, the charges stop flowing. The circuit is then said to be open or broken. Loose connection of wires or components in the circuit opens the circuit. Now, in a battery, the potential difference is measured in volts by an instrument called a voltmeter. When the cell is not connected to a circuit, the potential difference across its terminals is equal to its electromotive force. And so the electromotive force is also quantified in volts. Conventionally, potential difference is given as the voltage across the terminals when the battery is connected to an external circuit. The EMF and potential difference of a cell are different due to something called resistance that we want to look at. And to do that, let's go back to our water circuit. We know the pump signifies the battery and the water signifies the charges of the electrons. What about the valve? When the valve is 100% open, the flow of water is very fast. 50% it's reducing, and very slow at 25%. The valve regulates the flow through it. Equally, when an appliance like a bulb is in the path of a current, it offers resistance to its flow. In fact, non-conductors are absolute resistors, allowing no current through them. They are valves at 0% open. Good conductors offer very little resistance. Another thing, not all the force generated by the pump is used to drive water in the pipe. Some force is lost in driving water through the pump itself. Equally, some force is lost in the battery in driving charges through itself. And so, if you measure the voltage across a battery when it's not connected to an external circuit, it's higher than when the battery is connected or in a closed circuit. Why? Because some force is lost in driving the charges through the battery itself. So the battery offers internal resistance to the flow of current. And so the potential difference across two open terminals is known as the unloaded voltage. This is equal to the EMF. This EMF forces current to flow when a circuit is connected to the source of the EMF. There is typically some amount of resistance in all electrical components and devices. When no current flows, the voltage across the terminals of the source of EMF is no longer the unloaded voltage value. There is a voltage drop inside the device due to internal resistance of the battery. When the circuit was not connected, the battery had an unloaded voltage of 1.5 volts. Once the circuit was connected and current started to flow, there was a voltage drop due to the internal resistance of the battery and the voltage reduced to 1.3 volts. This is the potential difference of the battery. DC power supply is a commonly used device in the laboratory. It has the ability to create different amounts of EMF. As the voltage is increased, the potential difference across the terminals is increased. Note the unloaded voltage of the power supply is set to 5 volts. A DC power supply will experience a loss of potential difference due to internal resistance of the supply. When the circuit is connected and current starts to flow, the internal resistance of the power supply reduces the applied circuit voltage to 4.7 volts. The difference between the reading is known as the lost voltage. This voltage is lost because of the opposition to the flow of charges within the cell, what we have called internal resistance. Series and parallel connections. When two or more cells are connected to form a battery, the combined EMF of the battery depends on whether the cells are connected in series or parallel. How does cells connected in series different from those connected in parallel? Cells connected in series have the positive terminal of one cell connected to the negative terminal of another cell. This increases the overall voltage and hence the current. Shown here are 6 cells of 2 volts each connected in series to form a 12 volts battery. You can see that a series connection provides an increased EMF, and this is because charges gain potential energy from all the 6 cells as they pass through them. The combined EMF here is 12 volts, calculated by adding individual EMF. Cells connected in parallel have their like terminals connected together. The overall voltage remains the same, that is, they last for a longer time. If 3 12-volt cells are connected in parallel, the combined voltage for the battery will still be 12 volts. Shown here are 3 1.5-volt cells connected in parallel. The combined EMF of the battery is 1.5 volts. The charges flowing around the circuit will split into 3 equal portions. When they reach A, each portion passes through one cell only. So the gain in potential energy for each portion is therefore from one cell only. The advantage of this arrangement is that the cells will last longer before going flat. Bulbs also can be connected in series or parallel. These bulbs are connected in series. When a battery is introduced, all bulbs light with equal brightness. The same amount of current flows in devices connected in series. In this arrangement, when one bulb blows, all the others go off as well because this introduces a break in the circuit. However, in a parallel arrangement, damage to the bulb does not affect the others because they still have a complete circuit. More batteries will give more voltage, increases the current, and brightness increases as well. Chemical cells. Chemical cells provide electromotive force as a result of a chemical reaction. Primary chemical cells cannot be renewed once the chemicals are exhausted, while secondary chemical cells can be recharged. A simple primary cell or voltaic cell consists of 2 electrodes, one of copper and the other of zinc, dipped in a solution of dilute sulfuric acid in a glass vessel. On connecting the 2 electrodes externally with a piece of wire, current flows from the copper to zinc outside the cell and from zinc to copper inside it. The copper electrode is the positive pole and the zinc is the negative pole of the cell. The electrolyte is dilute sulfuric acid. So how does it work? At the zinc electrode, zinc is reduced to zinc ions and electrons are released. The zinc ions go into solution and electrons are carried along the conductor and thus current is generated. Meanwhile, the sulfuric acid dissociates into ions. When electrons reach the copper electrode, they combine with the hydrogen ions to form hydrogen gas. So over time, the zinc electrode dissolves away in what we call local action, and hydrogen gas bubbles are liberated at the copper electrode. The bubbles accumulate around the plate, providing an insulation called polarization, which opposes current flow and thus creating an internal resistance. Potassium dichromate is used to reduce this polarization. Local action is promoted by impurities of zinc and can be reduced by using pure zinc or coating zinc with mercury, a process called amalgamation. So this simple cell converts chemical energy into electrical energy. The Leclanche cell. In this cell, a carbon rod is placed in a porous pot containing a mixture of manganese 4 oxide and powdered carbon. The porous pot and an amalgamated zinc rod are placed in a glass jar containing saturated ammonium chloride solution. The ammonium chloride solution is the electrolyte, and carbon and zinc rods are the electrodes. The mouth of the glass jar is sealed with pitch so that the ammonium chloride does not seep out. So let's see how the electrodes get charged. Ammonium chloride, the electrolyte, splits into ammonium and chloride ions. The chloride ions move to the zinc rod and transfer their electrons to the zinc rod, forming zinc chloride. The zinc rod attains a negative charge due to excess of electrons. Therefore, the zinc rod becomes the cathode, the negative electrode. On the other hand, ammonium ions move to the carbon rod. The free ions of carbon rod neutralize the ammonium ions, forming ammonia and hydrogen gas. Consequently, the carbon rod attains a positive charge due to deficiency of electrons. It therefore becomes the anode, the positive electrode. The hydrogen gas is oxidized by manganese 4 oxide to form water, and polarization is prevented. Now, if an external copper wire is connected to the electrodes, the electrons will move from the cathode to the anode, generating electricity. The EMF of the Leclanche cell is 1.5 volts. The dry cell. A dry cell is the simplest unit of generating electricity. It generates electricity from chemical reactions, pumping electrons through wires. 2 or more cells form a battery. Substances such as acids dissolve in water to form charged particles, namely positive ions or cations and negative ions, the anions. These type of solutions form the electrolytes of a cell. Metal rods immersed in electrolytes act as electrodes. The positive electrode is the anode and the negative one is the cathode. These electrodes attract oppositely charged ions, resulting in a flow of electrons. Essentially, the dry cell is a modified version of the Leclanche cell. The parts of a dry cell may be understood by observing a vertically opened dry cell. The anode is a graphite rod. Graphite is a form of carbon. The zinc container is the cathode. The electrolyte is a moist jelly-like paste of ammonium chloride and starch enclosed in a metal cylinder as shown here. A mixture of manganese 4 oxide and powdered carbon surrounds the graphite rod. The jelly is prevented from drying up by sealing the top of the cell with a pitch. A cardboard washer is used to prevent the graphite rod from coming in contact with the zinc can. This is referred to as the spacer. The zinc can is surrounded by an insulating thick paper covering. The positive terminal of the cell is the brass knob at the top, while the negative terminal is at the base. The chemical reactions taking place are quite complex, but I have simplified them as appears on your screen. At the cathode, zinc is oxidized into zinc ions, releasing 2 electrons, which are collected by the graphite anode. The reduction reaction at the graphite anode is shown here. This flow of electrons produces electric current. This dry cell produces a voltage of 1.5. Barton cells and nickel-cadmium cells are better versions of the dry cell. Mercury-zinc Barton cells are used in watches, cameras, calculators, and hearing aids. The anode is the zinc powder and the cathode is the mercuric oxide. Nickel-cadmium cells are rechargeable cells. The lead-acid battery or the lead-acid accumulator. This is very commonly used as storage battery or secondary battery. The main materials required to construct a lead-acid battery include lead peroxide, spongy lead, and dilute sulfuric acid. The positive plate of lead-acid battery is made up of lead peroxide. This is a dark brown, hard, brittle substance. The negative plate is made up of pure lead in a soft, spongy condition. Dilute sulfuric acid used for the lead-acid battery has a water-acid ratio of 3:1. The lead-acid storage battery is formed by dipping lead peroxide plate and the spongy lead plate in dilute sulfuric acid. A load is connected externally between these plates. In diluted sulfuric acid, the molecules of acid split into hydrogen and sulfate ions. The hydrogen ions, when they reach the lead peroxide plate, receive electrons from it and become hydrogen atoms, which again attack the lead peroxide and form lead oxide and water. This lead oxide reacts with sulfuric acid and form lead sulfate and water. The negative sulfate ions are moving freely in the solution, so some of them will reach the pure lead plate where they give up their extra electrons and become radical sulfate. As the radical sulfate cannot exist alone, it will attack pure lead and will form lead sulfate. As positive hydrogen ions take electrons from lead peroxide plate and negative sulfate ions give electrons to the lead plate, there will be an inequality of electrons between these two plates. Therefore, there will be a flow of current to the external load between these plates to balance this inequality of electrons. This process is called discharging of the battery. Now we disconnect the load and connect the lead sulfate covered lead peroxide plate with the positive terminal of an external DC source and the lead peroxide covered lead plate with the negative terminal of that DC source. During discharging, the density of sulfuric acid falls, but there still is some sulfuric acid existing in the solution. This acid also remains as positive hydrogen ions and negative sulfate ions in solution. Hydrogen ions, being positively charged, move to the electrode connected to the negative terminal of the DC source. Here, each hydrogen ion takes one electron from that and becomes hydrogen atom. These hydrogen atoms then attack lead sulfate and form lead and sulfuric acid. Meanwhile, the negative sulfate ions move towards the electrode connected to the positive terminal of the DC source, where they give up their extra electrons and become radical sulfates. This radical sulfate reacts with the lead sulfate of anode and forms lead peroxide and sulfuric acid. Therefore, the battery is again ready for discharging.
The battery, of course, is now 200 years old and was discovered, it is said, by a fellow by the name of Aloisio Galvani, an Italian. Galvani was in fact lecturing to some of his pupils. He was a lecturer in medicine. Mrs. Galvani was standing in the one end of the room and she was preparing the evening meal because this was done at his home. And Mrs. Galvani was busy attentively listening to her husband, but also skinning the frog's legs. She noticed that when she touched the frog's legs, a twitch occurred. She called her husband over and said, "Have a look at this interesting phenomenon." And Aloisio Galvani came along, looked at the frog's leg, saw the twitch and said, "Wife, what a magnificent discovery I've made." Luigi Galvani wrote a letter to his friend Alessandro Volta. Volta was not a physician. He was what we would today call a physicist, or in those days they were known as natural philosophers. And what Volta did was decided to set up the experiment as Galvani had done, and realized very quickly that what had been discovered was not the essence of life, but some form of energy. And of course this was electrical energy. Now you see, the people of the day were not completely unaware of electricity. Electricity was known in the 1700s in the form of static electricity. Cuneus at Leiden University in Holland had done various experiments and in fact came up with a device known as the Leyden jar, the only device that was known at the time for the storage of electricity. The problem with this is it was static electricity. The experiments are always very brief in nature because of the short duration of the spark. The voltage is always high, so some of the experiments are a little painful and there's not much else you can do with it. These two Italians, they came along and they found that by the use of certain dissimilar metals and chemicals, you could generate electrical power on demand, at will. This opened up a whole new vista for research within the field of technology and science.